Hey everyone, welcome back to another related rates practice problem video. So let's dive right into this one. Right? So we filled a small paper cup in the shape of an inverted cone, kind of like those ones that you get in your water cooler sometimes, with water. But unfortunately, the water is leaking out of the bottom. Right? So what you've realized is that when the water level is 2 centimeters, the rate of leakage is 0.5 cubic centimeters per second. So the question now we're asking is how fast is the radius of the water changing at this moment? Okay? And some information we're given. Radius of the cup is 3 centimeters. The radius of the total cup is 3 centimeters. Height is 6 centimeters. And the volume of a cone is pi r squared h over 3. So let's dive right into it with our general picture. So there's two main uses that I like that the general picture really have for us. Firstly, so there's two main uses that the general picture has for us. So firstly, it sort of presents, it doesn't oversimplify anything for us. So it presents us only information that's true at every instant of time, right? If you remember that. So it doesn't oversimplify things for us. It allows us to make more objective decisions. Right? The next thing is I like to use it as a place to put in all my variables, right? All the variables that I've defined for this problem. So that kind of helps me keep track of what's what. Okay, so that's what I like to do with that. So let's go ahead and put in some variables here. So let's have the water level be somewhere like that. Um, if that's the case, then I know that this thing right here, this is going to be the height of my water, the water level, which I'm going to call h, right? I don't know what that is at any given point of time. I don't know what that is as a function of time, so I'm just going to leave it as h. The other thing I know is, the other thing I'm interested in is this radius, r. Let's call that r. And again, the reason I'm leaving these things in terms of variables is because I don't really know what these are as a function of time. I don't know what these are generally speaking. Right? So that's that. What else do I know that's true at any point of time? Well, the dimensions of the cup. Right? So I know for a fact that this cup is 6 centimeters tall, and the radius of this cup is 3 centimeters. So I know that, and that's not going to change, right? Because the cup doesn't get any bigger or smaller, so that's going to stay constant. So that's all my information that's true at any given point of time. Okay. Next, what I can do is I can draw my snapshot picture. Now, why the snapshot picture is so helpful is because it provides us a lot of information at one specific point of time, right? In this case, we're interested in when the water level is 2 centimeters. So this is going to be when h is equal to 2. Yeah. So it's 2 centimeters when h is equal to 2 centimeters. And this allows me to actually answer the question properly, right? This gives me the specific information that I need to answer the question properly, right? So we can go ahead and sketch in our snapshot picture now. So here I can put in a few more interesting details in addition to what's in here. So I know now that at this particular instant, this rate at which my volume is leaving is going to be 0.5 cubic centimeters per second, right? I know what that is. So dv dt, right, is going to be 0.5 cm cubic centimeters per second. Now, quick question for you. Is this going to be a positive or a negative quantity? Well, let's think about what V is as a whole, right? So if we define V to be like this volume inside the cup, right? That's what we've basically, I think we've defined it to be. If V is this volume inside the cup, as water is leaking, this volume is decreasing, right? This volume is decreasing. So as a result, this quantity is going to be negative. dV dt is going to be negative, right? So that's that. Another very useful piece of information that we know is that at this particular instant, as we've figured out here, my height is 2 centimeters. Okay, so those are two very useful pieces of information that I'm given that will help me get a specific answer to this problem. Right? Is there anything else? Unfortunately, no. So that's basically all my pictures now. So now let's actually go ahead and start solving my problem now and getting some equations down and such. Right? So the next thing we want to do is I like to go ahead and define myself a goal. Right? So just like with optimization, this kind of helps make sure that I'm doing what I actually meant to do in the beginning, and I'm actually answering the question. So in this case, I'm interested in how the radius is changing, right? So my goal is to find dr dt. So at the specific instant when h is equal to 2 centimeters. So that's what I'm trying to do here. So let's find an equation here that will help us do this. Let's find an equation. So if I were to come up here, remember that the volume of a cone is pi r squared h over 3. That looks like a great equation for me to use, right? So let's go ahead and just use that. So I have v. The only thing I'm going to do is I'm just going to bring the pi over 3 up front like this and multiply it to the rest of the terms. So we have r squared h. Okay. All right, so you might have noticed a little bit of a problem here, right? So pi over 3 r squared h, this equation has two variables, right? Two variables. So from the perspective of implicit differentiation, that's not a problem because we just do what we normally just have to do a product rule. But however, later down the road, this is going to give us a dh dt, right? Which is going to be a problem because we don't actually know how to deal with that. So one thing we're going to do is we're going to see if we can actually eliminate this h altogether to make life a little bit easier for us down the road, right? So that's what we're going to do. So let's come back up to our general picture here and see if there's anything in there that might help us. And right off the bat, you might see this. Notice that we have what look to be similar triangles here, right? So if I just connected these two dots and maybe these two dots, we have what look to be similar triangles, right? So if I could sketch these out a little bit more prominently here, you could see that we have this big triangle here, 3, 6, and we have this smaller triangle here with R and H, right? So we have similar triangles. When we have similar triangles, we can set up a proportion which will we can use to our advantage here. So if we come over here, we could say, okay, so we can say H over R equals 6 over 3, which is going to equal 2. Right? You could also do R over H equals 3 over 6, same thing. So given this, what I can say is that, okay, so if I know that h over r is equal to 2, I can say h is going to be 2r. Yeah? And now I have a relationship between h and r that I can use to eliminate h from this equation altogether. Now you may ask, why don't I just eliminate r? Because I have an r squared. Well, I'm trying to solve for dr dt, right? So it would be counterintuitive for me to remove the r. So the h is the one that I want to eliminate, right? So let's put that in there. Yeah. So what we'll have now is we will have pi over 3 r times r squared, and then we have this 2r. Distributing that is now going to be 2 pi over 3, bringing that 2 up front, r cubed. Right? So that's my new equation for volume. Right? So basically what we've done here is similar to what we actually would do in an optimization problem, right? Make this an equation of one variable. Now we can, quote unquote, make this equation move by taking our derivative with respect to time. We can make this equation move. Right? So if we do that, we will use implicit differentiation. So we'll have a dv over dt we'll have a dv dt on this left-hand side, and on the right, the 2 pi over, on the right, it's actually going to be quite nice. So what we'll actually end up with is we're just going to have 2 pi r squared, just using a power rule there, times dr dt. And remember, this dr dt is what I'm trying to solve for. Right? All right, so we've got this far. Now let's do a quick spot check, right? Let's do a quick check to see what we know, see what we don't know, and based on that, decide how we should proceed further, right? So dvdt we know, drdt we're trying to solve for, so that's fine. But this r I don't actually know anything about, right? So let's go look back to our snapshot picture and see if that helps us at all. So unfortunately, our snapshot picture doesn't have any information about r, but we do know that h is equal to 2. Right? We do that h is equal to 2 centimeters, and we also have this relationship between h and r, right? We have this relationship that we've established here, and we know what h is, so we can use that to solve for r, right? So I can take this guy, put him in here, and so what that's going to give me is I'm going to end up with, all right, so I have 2 equals 2r, and so what this is going to give me is r is equal to 1. Sweet. So now that I have that, I can pull that down here. It's a lot of green lines around here, but I can pull that down there. And so what this is going to give me, I can also plug in for dvdt now, which is negative 0.5, or it's negative 0.5, but I'm going to write that as negative 1/2. Right, so I'll have negative 1/2. It's going to equal 2 pi. R squared is just going to be 1 dr dt. And now I just divide both sides by 2 pi, and I will solve for dr dt. So my end result is going to be dr dt is simply equal to negative 1/4 pi. The units for this are going to be centimeters per second. Sweet. Now let's do one thing. Let's do a quick spot check to make sure that all of this makes sense, right? So if we come back up here, we realize that our answer is negative, right? This answer is negative. So if we come back up here to our general picture, what's going to happen as volume decreases? What's going to happen to radius as volume decreases? Well, it's getting smaller, right? So for example, the radius here at r is much bigger than the radius down here. Right? This radius is much smaller. So the radius is indeed decreasing. So naturally, this conclusion makes sense. So we are good to go. If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time!